Good day, everyone. I am Romero Buyo Jr. from Group 3, and I am assigned to discuss the topics on Chapter 4, columns, and other compression members. Structural members subjected to axial compressive loads are often called by names identifying their functions. Columns, the main vertical compression members in a building frame. So, ang columns is tanang vertical member nga naa sa usa ka structure. So, tanang vertical member sa usa ka structure is subjected to an axial loading. So, ang axial loading is um, perpendicular to all vertical members of the structure. So, columns is considered as a good compression member. So, ang chords in trusses, it is the outside part of the truss, vertical, in vertical position. So, okay sad siya sa pag-assist sa trusses into compression. Sa bracing members sa frame, nahimo po siyang aid sa usa ka frame nga para ma-resist ang compression. W shape having nominal depths of 350 mm or less are commonly used. These sections, being rather square in shape, are more efficient than others for carrying compressive loads. Deeper sections are more efficient as beams. Build-up sections are needed in large structures for very heavy loads that cannot be supported by individual rolled shapes. So this is an example of a column. For bracing and compression members in light trusses, single angle members are suitable. However, equal leg angles may be more economical than unequal leg angles because their least radius of gyration are greater for the same steel area. For top chord members of bolted or welded roof trusses, a pair of angles is usually unequal, with long legs back to back are used with or without gusset plates. Structural tees may also be used as top chord members for welded roof trusses. Column design and analysis are based on Euler buckling load theory, created by Leonhard Euler on 1757. So when a column is loaded to the buckling load or Euler load, a column will fail by sudden buckling or bending. The Euler's theory is based on certain assumptions related to the point of axial load application, column, material, cross-section, stress limits, and column failure. The validity of Euler's theory is subjected to a condition that failure occurs due to buckling. So, ang Euler's theory is nag-tackle sa failure sa usa ka load due to buckling. So, in other words po, sa Euler's theory, ug sa beam pa, since the beam is uh, perpendicular to a transverse load. So when the beam fail, it will create a deformation. So same rapod sa column. Since ang column is vertical, nakasubjected siya to actual loading if beyond na sa capacity sa column, then mo fail siya, mao na nang gitawag na to nga buckling or bending. So mo bend siya either left or right. So if the column is hinged at both ends, the Euler's critical load is given as this formula, this equation 4.1. So this Euler's critical load, mao ni siya ang magamit nato if naay i-assume na given load nga kaya sa column. Diha na to makita, ma-prove og sakto ba ang mo stand gihapon ang atong column dili siya mo fail sa given nga load. So diri pod sa Euler's critical stress, so mao ni ang formula kaning equation 4.2. So diri na i-test if og unsay maximum capacity sa usa ka column before siya mo fail. The modulus of elasticity term E implies that equation 4.1 and equation 4.2 are valid as long as the stress remains in the elastic region. This equation showed that the buckling stress is not a function of material strength. Rather, it is a function of the ratio L over R known as the slenderness ratio, SR. As the slenderness ratio increases, the buckling stress decreases, meaning that as a column becomes longer and more slender, the load that causes buckling becomes smaller. So for effective length, the restraints placed on columns and greatly affects its stability. To counter this effect, an effective length factor K is used to modify the unbraced length. KL is the effective length of the column. So, kanina, sa makita ninyo sa formula, instead na L lang ang diadire, if ever na i-restrain ang tumoy sa usa ka column, mao nang kailangan i-counter to para still dili makaapekto siya sa stability sa usa ka column. Mao ning effective length factor K is mabutang sa atong formula. So this is the effective length factors. Mao ni siya ang table. Makita rin siya sa libro sa Gillessania. Pages 159. Slenderness ratio. Steel columns are usually subdivided into two groups, long and intermediate columns, depending on their slenderness ratio. There are two values of slenderness ratios, SR sub x and SR sub y. For SR sub x, it is equal to K sub x times L sub x over R sub x. And for SR sub y is equal to K sub y times L sub y all over R sub y. The critical slenderness ratio CC corresponds to the upper limit of elastic buckling failure, which is defined by an average column stress equal to 0.5 Fy by substituting 0.5 Fy for Euler's critical stress in equation 4.3. So kaning slenderness ratio is usa pod ka importante nga um, part nga kailangan i-consider sa column kay mao man ni maghatag sa katas-on ug kabag-on sa usa ka column kay ug baga ra pod kaadyo nya mubuar ra pod dili pod economical. So og taas ra pod nya arang nipisa ra pod kaadyo arang ka prone siya into failure bisan gamay pag load nga ijang na kaya. This is yung maka-acquire sa iyang maximum strength ba nga ug unsa gadyoy basihan sa usa ka kolom. So this is the illustration for minor axis buckling and bracing. Limiting slenderness ratio. According to section 502.8, the limiting slenderness ratio KL over R for member whose design is based on compressive force preferable shall not exceed 200. For members whose design is on tensile force, limiting slenderness ratio L over R preferable should not exceed 300. So, importante ning dili mo exceed ining 200 and 200 for compressive force and tensile force for 300 kay prone na sila sa failure. So, this is the NSCP allowable compressive stress. So, this is for intermediate columns. And for long columns, mao ni sadya ang equation nga di allowed sa NSCP.
Good day, everyone. I'm Jericho G. Alumno. In continuation of the report of Romeo, uh, I am assigned to discuss about the remaining topics, which is first is the local buckling. So, local buckling of a plate element in a rolled shape or built-up compression member may occur before Euler buckling. The ability of plate sections to carry compressive loads without buckling is determined by the width thickness ratio B over T. If a shape is selected from NSCP tables, this ratio does not generally need to be evaluated. However, compression members constructed from structural tees, structural tubing, and plates must be checked. So, as you can see, natay table dire, mao ni ang mga H values nila sa width thickness ratios for non-compact. So, sa kini sa unstiffened elements ni og stiffened elements. So, if ever nga wa dire ang atong gi kuan gi design, so atong pangitaon ang width thickness ratio niya, which is B over T. So, compression members are divided into two, which is the stiffened elements and unstiffened elements. Stiffened elements which supported along two parallel edges. Examples are webs of W shapes and sides of box beams. And second is unstiffened edges supported along one edge only. Examples are flanges of W shapes and legs of angles. So, nata illustration, mao ni siya. Kining babaw mao ni ang stiffened elements and kining ubos is ang unstiffened edges. So, sa design na to, para ma-prevent local buckling, so naatay NSCP specifications, section 506.2, nag-require ni sila sa equation 4.10, which is kining B over T is less than or equal to H over the square root of Fy, which is the yield strength. So, kinahanglan nga ma-meet ni ang atong kuan plate elements para effective ni siya para ma-prevent na ang local buckling. So, for circular tubular sections whose ratios of outside diameter to wall thickness satisfies equation 4.11, just kini na sa ubos, are considered para effective siya. So kining circular tubular sections mo ni ani murag steel nga murag PVC ba type kana kanang lingin-lingin. So D over T is not less than 22,750 over Fy. Mo ni siya atong gamiton aron ma-effective ang atong design. So sa unstiffened compression elements, according to section 502.6.2.2, the allowable stress of unstiffened compression elements whose width thickness ratio exceeds the applicable non-compact limit given in equation 4.10 shall be subjected to a reduction factor. So if ever nga mas greater ang kuan wa di ma-prevent ang local buckling, so naatay reduction factor. So for single angles, mao ni ang naa sa katong inisipin nga kuan when 200 over square root of Fy is less than B over T and B over T is less than 407 over square root of Fy. So ang reduction factor is 1.340 minus 0.001702 times B over T square root of Fy. And when BT, B over T is greater than 407 over Fy, square root of Fy, so our reduction factor is 106,870 over Fy times B over T squared. So, naabot tayo reduction factor sa line pod nga members. So, for angles or plates projecting from columns or other compression members, and for projecting elements of compression flanges of beams and girders. So, makita po nato dire na sa libro which is page 163. Makita ta so natay reduction factor nga 1.293 minus 0.001177 times B over T times square root of Fy over Kc. So, kini mga unknowns dire makuha pa na to sa pagsugod pa na to solve kining Kc nga na. So, na kining ubos when B over T is greater than 512 over square root of Fy over Kc, then our reduction factor is 180. Formula sa atong reduction factor is 180,640 Kc over Fy times B over T squared. So, for stems of T's, mao gyapon ni siya mao ni ang reduction factor when tanay 33 over Fy yan na reduction factor is 1.908 minus 0.00272 times B over T times square root of Fy. So, when B over T is greater than 462 over Fy, square root of Fy, our reduction formula is 137,900 over Fy times B over T squared. Where ang atong Fy is in megapascal dyan na sa ang isang kuan. So, stiffened compression elements. Stiffened compression elements, so according to section 506.6.2.2, when the width thickness ratio of uniformly compressed stiffened elements except perforated cover plates exceeds the non-compact limit given in equation 4.10, a reduced effective width B shall be used in computing the design properties of the section containing the element, except that B over T need not to be taken as less than the applicable value given in the section. So for flanges of square and rectangular sections of uniform thickness, BE is equal to 664T over F times 1 minus 132.1 over B over T times square root of F, which is less than is dya sa B. For other uniformly compressed elements, so mao po ni siya kini nasa ubos kini ang atong gamiton, where B is the actual width of different compression elements and T is equal to element thickness, and F is the computed compressive stress in megapascal. Then if unstiffened elements are included in the total cross section, F for the stiffened elements must be such that the maximum compressive stress in the unstiffened element does not exceed FAQS or FBQS as applicable. So, allowable stress. So, the allowable stress for actually loaded compression members containing unstiffened or stiffened elements shall not exceed the following. So, kini, when KL over R is less than C, CE, CC rather, FA is equal to Q times 1 minus EL over R squared over 2 CC squared times FY over FS. So, money FS is equal to 5 over 3 plus na Q is equal to QS and QA. Cross sections composed entirely of unstable elements, so Q is equal to QS. Cross section composed entirely of stiffened elements, Q is equal to QA. Cross section composed of both stiffened and unstiffened elements, Q is equal to QS times QA. So when KL over R is greater than CC, so our FA is equal to 12 pi squared E over 23 KL over R squared. Kini atong FA is ang stress ni siya, allowable stress. So, ang next na to nga kan is ang column base plate. So, kining column base plate, mo ni ang kan natay steel nga kan column na to, which is na murag gipatong sa concrete nga kan. So, column loads transmitted to masonry and concrete foundations must meet the same bearing pressure limitations as beam loads. The required base plate area is area of plate is equal to column load over FP, where our FP is the allowable bearing stress of concrete according to section 510.10.2 of NSCP. So kinahanglan jud naa jud tay mga kuan aning atong laing libro aning NSCP, no, aron makita na to ang kuan. So makita ninyo nga naay lain-laing kuan, naay on sandstone and limestone, naay on brick in cement mortar, natay lain-laing yielding strength nila. Naay allowable bearing stress, naay laing bearing stress nila. Since kay lain-lain naman silang material nga gamit, nabo sa nila lain-laing allowable bearing stress. So support natay bearing stress nga 0.35 F prime C times square root of area 2 over area 1, which is dapat less than na siya sa 0.7 F. where na makita ninyo. So, mo ni ang illustration sa base plates. Kini mo ni siya. In determining the plate thickness under a double-shaped column, it is assumed that part of the base plate outboard from 0.95D times 0.8D rectangle acts as uniformly loaded cantilever. The allowable bending stress FB in the cantilever portion is 0.75 Fy. So, dire makita na to ang illustration. Muna yung double shape column on steel base plate. So, cantilever portion outboard from rectangle. So, FB is equal to MC over I is equal to 6M over BD squared, where B is equal to 1 mm, D is equal to plate thickness, M is moment at critical section, and M is given that Fp times x over 2 is equal to Fpx squared over 2. So Fb is equal to 6 times Fbx squared over 2 over 1 t squared is equal to 3 Fpx squared over t squared. So our t is equal to square root of 3 Fpx squared over Fb. So where x is the larger value of m and n, and Fb is equal to 0.75 Fy. So the actual bearing pressure under the plate is Fp is equal to column load over actual plate area. So in most cases, it is desirable to have m is equal to n. This will minimize the required plate thickness. So in the case where the column base plate is just large enough to accommodate the column profile, which makes M and N small. The column load is assumed to be distributed to an area much smaller than the base plate. The required thickness is determined as the larger of equation 4.28 or equation 4.29. So, kini nasa ubos. So, T is equal to the square root of 3 FPL squared over FB, where L is solved from equation 4.30 kinasabos. If L is imaginary, equation 4.29 is disregarded. So, mo ni ang among sa introduction sa among report. So, furthermore, natay illustrative problems which is ako ng kagrupo ban ang mo hatag. So, once again, thank you for listening. God bless you all.